Hey everyone, let's apply integration and the area between curves together to find the volume of certain solids of revolution. What we're going to do is we're going to consider the x and y axes and some curve y equals f of x. And to create a solid, we're going to rotate this curve about, let's say, the x-axis. Right? Pretend that's a perfect reflection. Right? Maybe I'll shift that down a little bit. Right? Something like that. Okay? And what happens when we do that, right, when we revolve it about the axis, is we get a solid that looks something like this. Okay, sort of like a vase, although it's got that hole at the bottom, right? And what we want to do is we want to find the volume of this vase. Well, we approach it the same way we approach finding the area under the curve. We divide this vase into cross sections. I'm going to do these in red so that you don't confuse them for parts of the curve. Right. So what we do is we partition the solid into n thin cross sections, each with an area function a of x and thickness delta x, which is going to turn into dx. You'll see what I mean in one sec. Let's consider a generic partition, or a generic cross-section, okay? Right, there's that guy. And it's just going straight across like that. Right? Not exact, right? This is not an exact estimate of the area, right? But we're taking an object, right? We're basically slicing this thing into pieces, or maybe I should say we're cobbling together various pieces and estimating this thing's volume by summing together these areas. Let me just highlight this guy's volume right here, right? This thing, right, has an area, right? This first circle has a certain area function. We'll call it a of x. You can then multiply a of x by the thickness of this cross-section, which we said was delta x, or roughly dx or whatever, right? And so when we do that, we get a solid with, that volume, right? And we can do that for each of the cross sections, okay? Right, and this right here, we'll call this, maybe I'll write at the bottom here, and maybe I'll just draw an arrow, right? This is the area of the first circle at x, right, at some coordinate x, maybe here, is a of x. Okay? So a cross-section at x, we can define its area function, a of x. And so what we can do is we can define the volume of a solid to be the quantity, the limit as n approaches infinity of the sum from I equals 1 to n of, and this is just going to be, look, the product of a of x times delta x, right? We just partition this thing into its little area pieces, right? And I guess they're technically solids, subsolids, because they have a thickness delta x. And we just add them up together. All right, we add this pink region right here to the next pink region right there, etc. We keep doing this. And we know from the definition of the integral that we're going to get the integral from a to b of a of x dx. So to find the volume of a solid revolution, we have to integrate the area. Now you might say, okay, great, what's the area function? Well, that depends on the curve we're given. Let's take a look at example 1. As with areas, I highly recommend drawing a picture. Right, we're taking the curve y equals root x, these two lines, and we're rotating it about the x-axis. So if we know that, then maybe we'll draw our y-axis a bit taller than normal because we know we're rotating about the x-axis, right? Y equals the square root of x, right? That we should know that graph, right? X equals 1. I guess that's this line right here, right? And it does continue to go like further up, right? It would go up above the curve, but really we're interested in the region, right? Y equals 0. Cut it off right there. You don't have to label it, but I'm going to, right? So we've got these, right? We're rotating it about the x-axis, right? So we try to get that roughly symmetric. It's about as good as I'm going to get it, right? And really, got that right there, right? And really, if we wanted to be a little more accurate, I suppose we could, even erase this line right here if we wanted. If, just wanted to see just the outside shell and not the inside, okay? And we wanted to find the volume of this bowl-like solid, right? So what you would do is you would say, okay, the volume is the integral from a to b. I'm just going to write this down again of the area dx. Now, we don't need to write that every time we do these problems, but just to remind you, that's what we're doing. We're finding the area. Maybe first we should find the bounds. Well, I think we can see that the bounds are going to be 0 to 1. But just to be clear, to find the bounds, let square root of x equal 0, right? Y equals square of x equal y equals 0. So x equals 0. Also note that x equals 1. They gave that 1 to us, right? So we don't need to find that. We just need to recognize it, right? So we have that the volume is the integral from 0 to 1 of our area function. Well, what is our area function? Well, if we take a look at a cross-section, don't worry about drawing the thickness piece. Just worry about drawing a circle, right, at like x, some coordinate x. What is the area function of that circle? You know what it is. It's pi r squared, right? Well, what's r? R is just the height of the circle, which is y equals f of x. So actually, this is going to be the integral from 0 to 1 of pi r squared. I guess I can write dx in red too, because that's the thickness, so to speak, right? Okay, so that's how you get the volume, right? That's the area function. It's just noticing, hey, wait a minute, we're finding a bunch of circle areas. That's what we're really integrating here. And a lot of times, the area is the area of a circle. In fact, just about all the time that we do these problems, the area will be the area of a circle. And the height of the circle is often related to the height of the function, or it is just the height of the function, right? And so at this point, we can say that this is the integral from 0 to 1 of pi times x dx, and that's a pretty easy thing to integrate at this point, right? We can just say, okay, this is going to be pi over 2 x squared 0 to 1. And so we get as an answer that our area is pi over 2. Or sorry, that our volume is pi over 2, right? Over and out. All right, so again, what did we do? We found the area of the curve. Or sorry, we found the area of the circle, and we integrated it, generally speaking. All right. We'll do example 2 in class. Let's do one more example here on this video right here. We can find the volume of a solid obtained by revolving the region bounded by the curves y equals x cubed, y equals 8, and x equals 0 about the y-axis. Now let's take a look at this really quickly. Y equals x cubed. That's another curve that we should know. Looks something like that. Y equals 8. Something like that. Okay? And x equals 0, right? Normally, x cubed goes like that. But since we've got x equals 0, we're cutting it off right here. Okay? Now we're rotating this about the y-axis. Maybe I'll make that a little steeper. Right? The higher degree polynomials are a little bit slower in the uptake until you get to 1 or so, right? Now note that this is a little bit different because our solid looks like this. Our cross sections run vertically. Right? Notice that. When we draw our cross sections, excuse me, or maybe I should draw a dotted line here, right? Right? They're going up and down, right? They're not going across the x-axis. They're going along the y-axis. So integrate with respect to y. With respect to y. Now the problem with that is that we were given the function y equals x cubed. That doesn't help us. We need x as a function of y. But that's okay, because we can just take the cube root of y. See how we reframed y as a function of x as x is a function of y? Okay. And that means that we're going to have, actually, we're going to write out, our volume function. Maybe I'll write it down here, right? V equals the integral from something to something of our area function, right? Well, what's our area function going to be? Well, it's going to be pi r squared. What's r? Again, it's just our function. Pi times the cube root of y squared dy. Now the question is, what are our bounds? We need to find our bounds. So find the bounds. All right? And note that we want to, in this case, because we're working with y, we want to let I guess we're going to let the cube root of y equal, right, that's y, equal 0. So y equals 0. Also, we were given that y equals 8. So really, our bounds are going to be from 0 to 8. And when we integrate this, we're just going to get the integral from 0 to 8 of pi times y to the 2/3 dy. And this is no problem to integrate. We're going to get pi, What is that going to be? There's going to be 3 pi over 5 y to the 5/3. And when we do that out, we're going to get 3/5 pi times 8 to the 5/3, right? We plug in 0, we're going to get 0, so whatever. And we can actually do a little bit better than this. This is going to be 8 to the 5/3 is 32, so we're getting 96 pi over 5. No need to include units as with area because we're assuming it's just cube units. Okay. So those are 2 examples for how to find the volume of a solid of revolution. Of course, we're going to go over a million more of these in class, but those are 2 to begin with. Try to do example 2. Try to have that ready for next class.